Hello everyone, my name is Naren, and in this session, let's learn how we can use Bloom filter for different use cases when writing your applications or designing complex systems. The main use case or the problem statement is, suppose if you have a list of some elements and you want to test whether a given element is present in the list or whether the given element is not present in the list. For example, consider that you are working on an email service in which you are trying to implement sign up endpoint. In sign up endpoint, you also need to provide a feature where user can test whether that particular username is already taken or not. Consider these are the list of username which is already taken. Now there is a user who is trying to guess or check whether this particular username, like @gmail.com, this particular username is already taken or not. What is the data structure which will help you to check this particular username is already taken or not? So the first thing we can try is list. Now we have list of all the usernames, and then we can check this particular username is already taken or not. In this case, we need to hop on each and keep on checking each and every element in the list, and then check whether this particular element is present or not. If it is not present, that means that this username is not taken. But the problem here is you need to check or iterate through each and every element in the list. That would give us time complexity of order of n, and that is not good. Also, the other problem is if we are planning to distribute the servers for our email application, and that's when the real problems start. We can't maintain this list distributed in all of the servers, or we had to have one central repository or one central machine where it holds the list of all the username taken. And that's not good too. What other data structure can help? In that case, we can think of hash tables, right? What we need to do is hash each and every username taken in the hash table. And then whenever we want to check a particular username is taken or not, in that case, hash this or check this element present in the hash table or not. And that works. I can see 2-3 problems in hash table also. The problems are, first one, the time complexity is not always order of 1. Everyone says that hash table, the time complexity is order of 1. But when there is a hash collision, it needs to do linear probing. In that case, it's not always 1 out of 1. That means that it's the checking is not always constant time. And also one more problem is, since hash table is going to grow bigger and bigger, the memory it takes will also be huge. And the only good thing is we can maintain some central hash table, or distributed hash table, which can help in distributed kind of distributed machines. But the storage is always a problem. And also, when the hash table takes a lot of storage, we will be storing that particular data in the disk. In that case, reading the data from disk always take a lot of time, and it adds some of disk I/O operation also, plus storage. And these are the problems of hash table, and this is the problem when we are using list. So what other data structure we can think that helps to solve this kind of problem, which gives us efficient solution? That's when Bloom filter helps you. Bloom filter is probabilistic data structure, which is somewhat similar to hash table. Bloom filter is everywhere. It is used in most of the famous applications and most of the famous databases. Now remember, I said that it is probabilistic data structure. What that means, let's say you want to check this particular username is present or not present. Now you can ask the question to Bloom filter, say Bloom filter, you're going to ask this question, this particular username is present or not. The Bloom filter can answer two ways. It will say it is present or it is not present. It can answer two ways, right? Either it is not present or it is present. When it answers, look at the confidence level of the algorithm. When it says it is not present, it is 100% sure that this particular username is not present. But when it answers that this particular username is present in the list, it is not 100% sure. It is somewhat like say 90% sure that it is present, but 10% there is a chance that it is not present. But when it answers that this particular username is not present, it is 100% sure. You can completely believe Bloom filter that that particular element is not present. That's why we call Bloom filter as probabilistic data structure. There is somewhat probability when it says that particular element is present. That's why we call it as probabilistic data structure. The advantage of using Bloom filter is it takes a lot less storage than any other data structure like hash table. And since it takes a lot less storage, we can save the data of the Bloom filter in memory, and then we can run some computation a lot faster than any other data structure. If you go for hash table, it takes a lot of storage. And when it takes a lot of storage, the data will be stored into disk. When the data is in disk, the read and write operation will take a lot of time. And that's why Bloom filter is best algorithm to do or use whenever we want to do membership check. Let's see how Bloom filter works and what are the components you need to make this Bloom filter work. First, you need a bit array of certain length in which each boxes represent a particular index. And also you need two hash function. Basically we take many more hash function. For the simplicity purpose, I'm going to take only two different hash function. Okay, and this is hash function 1 and hash function 2. And obviously you need input data to save into the Bloom filter. Okay, now what you need to do is say this is the first input we are going to save in the Bloom filter. Now when you get this input, pass this input to these two hash function, and these two hash function will generate a unique number. Consider when I pass this cat into these two hash function, we got 2 and 6. 2 and 6 as the hash function. This is the output of hash function 1, and this is the output of hash function 2. Now what we need to do is go to index 2 in the bit filter and then set that particular index. So I'm going to set these two places with number 1. I'm going to set this bit to 1. Okay. And also one more prerequisite is consider we have zeros in prior in all of the bits. Okay, consider the bit array had all of zeros. Now once you pass the first input to hash function, we got 2 and 6. Set this respective index to 1 and respective index to 1. So 2 and 6 index are set to 1 and 1. So next, let's save dog also into the Bloom filter. Now consider we got 4, 10 as the output of these two hash function for the input dog. Now what do we need to do is go to these two indexes and then set those index to value 1. So we need to go to 4 and 10 and set the values to 1. And then 1. Okay. Now let's also save rat into the Bloom filter. Okay. Now consider we got 10 and 19 for the input rat. So this is the output of hash function 1. This is for hash function 2. Now let's set the respective indexes to 1 also. Now if you see, this hash function also gave 10, which is already set by the dog. That's not a problem. Still we go, we see it's 1, we don't need to set it. And for 19th, we go here and set this value to 1. Okay, done. Now we have enough data already saved in the Bloom filter. Let's check a particular input is present or not. Consider we got input dog. Okay, now we need to check dog is present in the already saved data or not. So we have the Bloom filter here, and so this is what we consider as Bloom filter. This bit array is what is the Bloom filter. Now when we get the input, okay, which we want to check whether that particular data is already there or not, we had to pass this input to the same hash functions, that is these two hash functions, and get the output. Obviously, for dog, we get 4 and 10 because every time it works the same way. Earlier also we got 4 and 10, so now also we get 4 and 10. Go to those position 4 and position 10, and see if both the places are set to 1. If it is set, that means that we have this particular element. Now, when we go to position 4 and 10, there is 4 and there is 10, we can see that both positions are set. That's when we can easily say it is present. But remember, I'm going to give you one more scenario that will tell you the probabilistic nature. For now, think dog is present in the given data because we saw that is 4 and 10 is set to 1 and 1. Let's check one more input. Say cow. We got cow. For cow, when we run this cow into these two hash functions, what do we get? Say we get 19. Say we get 19 and 23. So this is the output of hash function 1, and this is the output of hash function 2. Now we need to check whether this particular input is present in the Bloom filter or not. Okay, what do we need to do? Go to the position 19 and 23 and see if both bits are set to 1 or not. Go to 19 position here and 23 position here, and you can see, okay, you can see that both positions are not set to 1. That means that it's not there. Why? Because if we had processed this earlier, or if we had saved this in the Bloom filters, we would have gone to these two positions and set this position to 1, right? But since we didn't get in the first as an input, we haven't saved or we haven't set those respective position to 1. So that's why we saw 0 here. And that's why it is actually not present in the Bloom filter. We can say this is not present in the input data or the data which we have saved so far in the Bloom filter. Let's take one more example. Say we want to check this particular input is present or not, that is hen. So now you need to pass this input to hash function 1 and hash function 2. What do we get? Say we got 19 and 2. So this is the output of hash function 1 and this is the output of hash function 2. Now what we need to do, go to these two positions in the bit array and then check if both bits are set to 1. If it is set, that means that it is present. If it is not set, it means that it is not present. It's not like both shouldn't be set. Even at least one hash position, if it is not set, that means that for sure we don't have this particular input in our storage or in our Bloom filter. So what we need to do, go to 19 position. Yeah, it's set. It is set. Go to 2 position. That is here. It is set. But did we even process hen, or did we even save this particular input in the first place? We didn't save it, right? But why both bits are set? That's because 19 position was set by rat and position 2 was set by cat. There's a collision, right? And that's the reason why we call it as probabilistic data structure. But the membership test, when the Bloom filter says that it is not present, for sure it is not present because either of these two index will contain 0 in it, right? That means that for sure we haven't saved it because there will never be a collision in that case. So we are 100% sure when we say some element is not present in the Bloom filter, but we're not 100% sure. We are like maybe some percentage. We are saying probably this guy might be present in the Bloom filter. Now, what is the time complexity? How do we calculate it? So we took how many hash function? We took only 2 hash function. Most likely we will not be taking 2 hash function. It will be even more. The more hash function we take, the more probabilistic answer we get. The less hash function we take, the more collision happens in case when we are checking whether that particular element is present in the Bloom filter. So I took only 2 hash function just to make this explanation simpler, but ideally we'll be taking more. So let's take let's consider we took k number of hash function, okay, and when we are doing operation, we'll be checking in the Bloom filter or bit array k times, right? So every time when we do search or when we check, we iterate or we go to k position. That means that the time complexity is order of k, and this is constant because in that particular Bloom filter we always keep the same number of hash functions. So the time complexity is always constant and it is equal to order of k. And also if you see the storage, Bloom filter took is only this bit array, only this bit array. And we need to also say what kind of hash function we are going to use. And this is much simpler, right? And this is always constant. The only thing is this bit array. Instead of taking bit array, you can take bit representation like 0, 1, 0, 0, 1, 1. And when you convert this into base 10, you will get, say, 23 or something like that. So you can take binary representation of the data structure in whatever language and then convert that into integer and you get this output. This output is considered as the Bloom filter. So whenever we want to save the Bloom filter data, we just need to save this output. That's it. It's that. Only the size is like, in this case, it will take maximum of 8 bits, and 8 bits, it will take about 2 bytes, right? But most likely the Bloom filter will not be this short. It will be even bigger, even though, for example, if it takes about 10 characters or 10 numbers in it, it would take about how much? 10 bytes, right? So that's why Bloom filter is so efficient. When you have 10 bytes, you can save it in memory and then the operation will be a lot faster. The disadvantages of using Bloom filter is you need to know the expected size of input, or say if you want to save about 10 million or 10 billion records, we will have to keep that much bigger bit array or bit representation in memory already pre-allocated. And here is the approximate calculations of how much memory you might need to save the Bloom filter to save 40 million records. We might require 159 MB of storage to save this particular Bloom filter. That is the bits representation of the Bloom filter. So we will need about 159 or 160 MB of storage to save this data once we process a number of data or 40 million records, okay? And also we might end up needing 23 different hash function to arrive at the probability of mistakes, like 1 mistake in 10 million queries, right? And that's cool. Like there will be only one mistake in 10 million queries when it is trying to find a particular record, whether it is present in the Bloom filter. And there will be no mistakes when it tells that definitely this particular element or record is not present. But there will be one mistake out of 10 million times when it says that yes, this particular element or this particular record is present in the Bloom filter. So I'm not going to explain the formulas to calculate this data or how much storage is needed or how many hash function we need to take to reduce the mistakes. And I'm going to leave this link over here. You can go to this link and change different parameters and arrive at the answers. And there is also formulas available there, how these particular numbers are calculated with all the nice statistics shown there. So what are the applications of Bloom filter? Bloom filter can be used anywhere, wherever you want to check whether that particular record is already present in our system or not. Say, for example, Apache HBase, Apache Cassandra, and Postgres databases are already using Bloom filter to check or to make sure that particular record exists. If it exists, then only they will go and fetch that record. Say, for example, when you're doing select star by some ID equals to 100, what they do is they would have calculated the Bloom filter for all the tables with that particular ID. Or when you do the query, like select star by ID, they check that particular ID is already present in the Bloom filter. If that ID is present in the Bloom filter, then only they will go into the table, and in the disk, they will fetch that particular data. So that way, they are saving a lot of time in searching for that particular record with that ID 100. If it is not there, they will, by the help of Bloom filter itself, they will say that particular record is not there. And that's how DBs are optimized. And also, Google is using Bloom filter to help browsers fight against the malicious URLs or websites. How they do that? So all the identification of malicious URL happens on the Google server. Google, every week or every month, they will be having a huge list of all the URLs which are not safe to browse. That would be up to about 50 MB in size. Say they have 50 MB in size of list of all the URLs which are malicious. Now, obviously, when people browse through Chrome browser, they will need to, the browser need to check whether this particular URL, a particular user is browsing, is not malicious URL. How do they do that? They can't get the very updated list of malicious URL every time or every week once, because the list is 50 MB in size. The data is costly, especially in some countries, poor countries, right? So what instead Google does is Google calculates the Bloom filter for the list of all the malicious URL, and it generates a Bloom filter which looks something like this, right? 3, 4, 5, 6, 7, 8, 4, like a big number. And it just sends this number, which would be about 1 MB in size, to all the browsers. That way, browser has the Bloom filter, and browser also knows what are the hash function which are used to calculate that particular Bloom filter. So whenever a user visits a particular link or a URL, what browser does is it calculates the hash for that particular URL and check against the existing Bloom filter to check whether that particular URL is malicious or not. That way, the whole 50 MB data is not transferred from Google server to all the different browsers or the customers or the Chrome users. So instead, just the Bloom filter was sent to the Chrome browser. That way, we saved a lot of bandwidth for the users, and it was pretty quick. The other applications are like medium.com uses it to check whether this particular user story or blog was already recommended to the user or not. If it is, say, Medium maintains Bloom filter for each and every user, so that way it is a lot easier to check whether this particular article or blog was already recommended to the user or not. Before recommending it to the user, they will check in the Bloom filter. If it is already is there in the Bloom filter, they are not going to recommend. If it is not, they will recommend. And similarly, Bitcoin uses Bloom filter to synchronize the wallet. I think I have pretty much shown you how Bloom filter works and what are the applications. Next time when you are implementing some software or some application, please feel free to use Bloom filter because it is efficient and it is very good in checking that particular element exists or not. If you like this video, please share this video with your friends. Hit a like button, comment, or if you have any suggestion, please post it to me. Thank you. And obviously, subscribe to my channel if you haven't subscribed yet. Thanks a lot.